Some molecules are more complex than the molecules seen previously. They branch off, often in multiple locations, forming a very crazy-looking molecule. In the following examples, refer to these 4 steps in our strategy.
Alright, now, let's draw a 3-methyl-4,6-dipropyl 1-decyne. Whew, it's an ugly one. Let's get down to business. Alright, so the first thing that we're going to look at here is the parent chain. The prefix deca means that there are 10 carbons, so let's draw those out. Alright, it ends in YNE, which means it's going to contain a triple bond. But where? Bond number 1. So if this is bond number 1, that means that the direction of numbering is going to be from left to right. So let's number these. Next, we're looking to label our substituent groups. Methyl means 1 carbon. That's the prefix meth. YL just means it branches off of this main chain. The meth group comes off of carbon number 3. Dipropyl means there are going to be 2 propyl groups. The first propyl group will be at position 4. The second propyl group will be at position 6. Let's draw them. Now recall that each carbon has to form 4 total bonds. Each hydrogen can only form 1 bond. 1, 2, 3, 4, 5, 6. Whoops! We've made a mistake here. There is a shorthand notation that doesn't involve drawing every single individual hydrogen, but for the time being, let's start by labeling each hydrogen separately. All right, let's do another one. Same as before, our first step, identify and draw the parent chain. Octa means 8, so there are 8 carbons. Ane, A-N-E, means all single bonds. Now for the 3-ethyl group, ethyl means 2, so we are going to put the ethyl group on carbon number 3. Let's fill out our remaining hydrogen. Clean these up a bit. Alright, so it doesn't particularly matter whether you project the methyl or ethyl groups up or down. This is a 2-dimensional representation of a 3-dimensional molecule. So in essence, both can be right and both can be wrong. I like to orient them in such a way that they're always as far apart from one another because they are made up of electron pairs, those chemical bonds, and electrons repel one another. So I try to make sure that they're as far apart as possible by alternating them on either side of the main chain. Now you might also notice how many total carbon atoms there are. 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17. So this is C17, recall. There's our structure, there's our formula. Let's clean up our second example. Notice how we've condensed our structure in our final draft here, instead of drawing each hydrogen individually. 10 carbons. All right, team, let's name this compound. Our first step, as always, identify the longest chain. Our next step is to identify the substituent groups. When naming a compound, our parent chain comes last. In this case, 6 carbons would be hexane. This is a methyl, this is an ethyl, and this is an ethyl. Now we count our carbons in the parent chain to give each of these substituent groups a home address. All right. All right, so let's break down this answer. Number one, we don't always have to count from left to right. We can count from right to left. The reason that we would count from right to left or left to right is to get the smallest numbers possible. If we count from right to left, we get 2, 4, 4. If we were to count the other direction, 2, 4, and 4 adds up to 10. 3, 3, and 5 adds up to 11. The smaller numbers is our answer. Have you ever wondered why the acetate ion has such an interesting look to it? The carbons and oxygens are separated, but the hydrogens aren't. I wonder why that is. The answer to that question is that this is a structural formula. The arrangements of the elements in the formula give us a clue as to the structure of that compound. We'll be getting more in detail on how to draw these Lewis diagrams a little bit later. Let's take a look at another one. There's a general rule when drawing these diagrams that you're allowed a maximum of 8 electrons, or an octet, around the element in the compound.
When sketching out molecules with a repeating pattern, we can often simplify the sketch using abbreviations. Note the expanded structural formula, which we've seen so far, the condensed structural formula, which we've also seen introduced earlier in this video. Here are 3 different ways to express the same compound, 3-ethyl 2-methyl-hexane. We have the expanded formula that involves showing every individual bond, the condensed formula, which groups all of the hydrogens around each individual carbon, and finally we have the skeletal structure, where each vertex of the line, each point where it changes direction, represents a carbon and the appropriate number of hydrogens. When expressing the molecular formula, as we've seen previously, we can be describing many different compounds that contain the same molecular formula. We call those isomers. Structural formulas are more specific. Each compound has a unique structural formula, which can be expressed one of 2 ways, as we see demonstrated on the page.